Okay, so now we come to the Michelson Morley experiment. Don't be too worried here about all the math you see on the board. We're just going to do a quick reminder about a few things here, most of which we covered in the math review. But for those of you taking a more qualitative approach to the course, we'll use our Festina Lente motto, as it were, make haste slowly. So we're not going to try to rush through this. For those of you for which some of this is old hat, you can fast forward as you wish, of course. So Michelson Morley experiment, before we do the quick math review or math reminders here, really, the goal of this was to detect the ether wind that pretty much everyone thought should exist. So we'll come back in a few minutes to actually talk about what that was, why they're looking for it, and so on and so forth. Let's just do this quick overview of math reminders, because this really is the first topic that will be more mathematical. But remember, it's all algebra. We'll do it step by step, so that, again, for those of you who may be taking the more qualitative approach, the goal here is to follow along, see where we end up, and understand the concepts involved. And for those of you who like the more quantitative approach, then we can dive into the math a little bit here. So just a few math reminders, notation to start off with. When we have 1 over a just being some number, representing some number, a symbol representing some number, it could be x or b or whatever we want to do there. So 1 over a, we also write that as a to the negative first power, a to the negative 1. 1 over a squared, a to the negative 2 power. Square root of a, write that as a to the 1/2. Square root of a times the square root of a gives us a back again. 1 over the square root of a then is 1 over a to the 1/2 equals a to the negative 1/2. And so on and so forth with things like that. 1 plus a squared clearly means 1 plus a times 1 plus a. You could multiply that out, do the cross multiplication there, and get an answer. 1 plus a to the nth power, where again, n is just some number here. Typically an integer, 1, 2, 3, 4, 5, that type of thing, but doesn't have to be necessarily. That means 1 plus a times 1 plus a times 1 plus a times 1 plus a n times. So if this was 5, it'd be 5 times you'd have to multiply it by. Clearly that gets sort of messy, and in a minute we'll see a way to get around that in certain circumstances. When we're adding fractions together, a over c plus b over d, for example, remember how we use the little mathematical trick? We can multiply to get a common denominator here, so we can add the two fractions together into one fraction. We can multiply each term by 1 in the form of d over d in the first term, so giving us cd in the denominator on the bottom, and then c over c for the second term, again multiplying by 1, giving us dc or cd on the bottom. And so then once we have the common denominator in the there, we can just add them together, so we get AD plus BC over CD, and I just did a little quick example here. If we're doing 3/4 plus 2/5, you can see it works out to 23/20 there. Another thing that we'll encounter form here is if we have A minus B, we can factor out the A from each term. So this would be A times 1 is A, and then A times B over A is just going to be B. The A's cancel. So A minus B is the same as A times 1 minus B over A. Or the form we'll actually see is this, A squared minus B squared. We can factor out an A squared from each term, so leaving a 1 for the first term. A squared times 1 is A squared. And for the second term, A squared times negative B squared over A squared. The A squareds were canceled, just leaving us the B squared there. And before we get to this, then also one other form like this, which this is actually what we will see here in a little bit. Square root of a squared minus b squared. We'll use this little mathematical technique. So factor out the a squared, all under the square root sign. A squared times 1 minus b squared over a squared. Then, if you have the square root of two products, if you have the square root of like x, y, you can do that as the square root of x times the square root of y. So that's what we did here. We have a squared times 1 minus b squared over a squared. So that's the same as square root of a squared times the square root of 1 minus b squared over a squared. And the square root of a squared is just a. And we're assuming here that a is a positive number. We're dealing with positive quantities here. And then that leaves us square root of 1 minus b squared over a squared there. So a little bit of simplification there. So most of that we did in our math review. Something we actually didn't do in our math review that's going to be helpful this time is something called the binomial expansion. We're not going to try to prove this or get into the details of why it's called binomial expansion. We're just going to use it. It's a type of thing that physicists love to use all the time when they can, because it enables us to simplify very complicated expressions. So here's how it works. If you have 1 plus a to the n, so again, this type of situation here, it's 1 plus a times 1 plus a times 1 plus a times 1 plus a. If a here is a very small number, a small positive number, and if we say a is much less than 1, that's what this symbol means, much less than, instead of just less than, it's much less than 1. So a is very small compared to 1, down near 0, but not quite 0. Then 1 plus a to the nth power, this whole thing we'd have to write out, becomes very simple. We can write it as approximately equal to 1 plus n times a. In other words, take the exponent here, whatever that is, maybe it's a 3, 1 plus a cubed, so this would be 1 plus 3a. Or if we have 1 minus a to the nth power, and again, a is much less than 1, it becomes, because we have a minus sign here, 1 minus na. Or even 1 plus a to the negative n power, again, because you're essentially multiplying the exponent times whatever the a value is, assuming, again, a is much less than 1, it's 1 minus na. And this is known as the binomial expansion. So anytime we can do something like that, replace a long multiplication with something simple, and remember, it is an approximation. It's not exactly equal to it, but it's close enough usually for what we want to do, as long as a is much less than 1. And in the special theory of relativity, we often have, maybe not often, but we have a number of cases where a here is v over c, a velocity. So we'll see that a will have like 1 plus v over c, or 1 plus v squared over c squared, where c is the speed of light, and v is just another velocity. And so in many cases, if the velocity is less than the speed of light, much less than the speed of light, and often is, then we can do this substitution. And it's called the binomial expansion, because we're expanding this out in a series of terms. That's where it comes from. We're actually only using the first two terms. There would be more terms in the series here, but first two terms are usually good enough for what we want to do. Okay, so that's just a relatively brief review, some reminders of the math we'll be encountering. Again, we'll try to take a measured pace here and do many of the steps, so you should be able to follow along. But if you're rusty with some of this, you might want to just jot some of this down, play around with it a little bit, and hopefully knock some of that rust off. So let's talk about just the basic idea here of the Michelson Morley experiment. We're going to break this up into several parts, so that if we did this in one long video clip, it'd be a while here. So we don't want to do that. So we'll do it part by part. Okay, first part is we just want to understand, what's going on here. What were Michelson? It was Albert Michelson, Edward Morley, 1880s. Michelson did an earlier version in 1881 of this. The more classic version, 1887, is more precise. He was able to fix up it a little bit in terms of how precisely he was able to measure things. So this is a case for those of you who are interested. Maybe you're in Ohio. It was actually at what became Case Western University in Cleveland, Ohio. And their goal was to detect the ether wind. So to remind ourselves about a couple things here. Remember we were talking about the speed of waves, wave speed, and several key facts about wave speed. One of them, or maybe we'll do two of them here. So when you're talking about wave speed, and of course eventually we're going to apply this to the speed of light, because that's what Michelson and Morley were dealing with, the speed of light. So when we think about wave speed, remember we talked about the movement of the source. So if you have a light source, or we did examples with a source with water waves, a paddle, like in our long tank of water, paddle moving up and down, generating those waves such that what happens to the wave speed then? Nothing happens. It's still whether you're moving the paddle, the source of the waves, through the medium, the water, or the paddle is just standing still and generating the waves, the speed of the waves traveling through the medium, through the water in this case, is going to be the same. Now it does affect, remember, the wavelength and the frequency of the waves, but does not affect the velocity of the waves, the speed of the waves through the water. Same thing with light. If you have a flashlight, some source of light, and you measure the speed of light coming from that flashlight as it goes by you, and then you bring that flashlight, speed up on a truck or something, a very fast jet plane, and you watch it moving by, and then you measure the speed of the light from that flashlight going by. It is not the speed of the plane plus the speed of light that you measure. You still measure just the speed of light as it was. So the movement of the source does not affect the velocity of the waves. But what does affect the velocity of the waves, at least in principle, is the movement of the medium. The movement of the medium does affect the velocity of the waves. And again, the water examples we used, remember, were such that if you have a wave traveling through water, say in a still pond, and you're the observer, you're measuring the speed of the wave traveling across the water, traveling through the water there, you get some value. If you then take the exact same wave and generate it, but generate it in a moving water situation, such as a stream, a river, something like that, the speed of the wave will be the speed of the wave through the water, of course, through the medium, but then also you have the velocity of the medium adding to the velocity of the wave. And so in that case, you will see a difference in the velocity of the wave from the still situation where it's just traveling through the pond, say, or a tank that's still, versus if the tank is moving or if you're in a situation where the river is moving, then the movement of the whole medium, the movement of the water itself, carries the wave along. So if I'm on the bank observing it, I see the water going by faster. And of course, intuitively, it makes sense like that. Or if I'm going upstream, right, then if the wave is going upstream and the water is moving the other direction, then it's slowing down the wave. Okay, so that's the idea of wave speed. And two key facts about wave speed. How does that apply to the ether wind? Well, remember the luminiferous ether was the idea that if light is a wave, it has to have some medium. Something has to be actually doing the waving, the oscillations. And the idea it was the ether. Remember, if you want, you can spell it with A-E-T-H-E-R here if you want, but we'll just use E-T-H-E-R. That's actually how it's used in the multivolume series of Einstein's correspondence. So they chose to use E-T-H-E-R, so that's why I chose to go along with them, but there are many other books that use the A-E-T-H-E-R, so it's not that big a deal. Anyway, so side point there. Movement of the source versus movement of the medium. Let's apply that to light then. Okay, so now we're talking about movement of the medium is the ether. If the ether is sort of the stationary background for the universe is just sort of consists of the ether and then everything in it, the Earth moving around the sun and then rotating on its axis as well, so it's revolving around the sun, rotating on its axis. Clearly, as it moves around, it must be moving through the ether. And so that would be like a situation where essentially if I could feel it, if I'm on the surface of the Earth, depending on the orientation, I would feel the ether flowing by me, or I'd really be flowing through the ether, moving through the ether. And so depending on my orientation, if I say, just for the sake of argument, say I was moving through the ether this way, so if I could feel it, I'd feel it coming by this way. But in another direction, I wouldn't feel it depending on my orientation. And so that's what Michelson and Morley set out to try to test a little bit to see, could we determine how we're flowing, how we're moving through the ether wind as the Earth moves around the sun at about 30,000 meters per second, I think is the figure. So we should feel, again, we can't feel it, but if we send a light beam, basically, so here's our light beam, and we're going to send it maybe into the ether wind versus sending a light beam the other direction, maybe with the ether wind. So we'll assume, let's just say, we'll call this the ether wind. And again, that wind is going to be generated just by the motion of the Earth around the sun. And clearly, we're not always going to be directly into it depending on how we're standing and where we are on Earth at any given time, et cetera, et cetera. But you can take all those effects into account. So we'll just do the simplest situation. We'll assume going into the ether wind here, we're either sending a light beam into the ether wind or with the ether wind. And from our basic wave speed fact, the movement of the medium in this case should affect the velocity of the light. In other words, if I'm an observer here, I should be able to detect the difference in the velocity of light depending on which way it's moving in the ether wind. And so that's what Michelson Morley set out to do. And so in the next video clip then, we're actually going to set it up and start doing a calculation just to see what their result was and why it was so significant. So part 2 of the Michelson Morley experiment. And what we're going to do here is we're going to set it up actually using an airplane example. And the reason for doing that is it's just a little more intuitive for us. Sometimes when we do it with things we're not used to thinking about so much, for example, light waves, just the strangeness of the situation can give us some conceptual problems or challenges. And so we'll just do it with an airplane here. The analysis, though, will work exactly with light waves, and I'll explain why in just a second here. Let's set this up. So imagine we have an airplane. We're going from A to B and then back again. So round trip, first leg up to B and then back down to A. We'll say our plane has some velocity, v sub plane, or we'll probably just use v sub p for the plane velocity. And then we have a wind involved. Actually, we're going to do no wind at first, but then we're going to turn on the wind, as it were. And the wind's going to go directly in the face of the plane on the first leg of the trip, and then it'll be with the plane, helping the plane on the return leg. So clearly on the first leg, when there's wind involved, the wind will retard the plane's velocity, so it'll be going a little slower. And just as, if you've traveled by plane before, sometimes the pilot will say, hey, we have a tailwind today, so we're able to make the trip a little faster than normal. Sometimes we're battling headwinds, and therefore it'll be a little slower. That's what's going on here. So on the first leg from A to B, battling headwinds, and so it's going to be slower. The effective velocity of the plane will be the velocity of the plane minus the velocity of the wind. And then on the trip back down from B to A, then the plane will have added velocity because of the tailwind, so it'll be the velocity of the plane plus the velocity of the wind. Before we get into that, though, let's do the no wind case. In other words, how long will it take the plane to make a round trip from A to B and then B to A back again? Well, we know that velocity, or not velocity, but time traveled is just distance divided by velocity. Again, remember if you have to go, if you're going 60 kilometers, right? Let's just say 120 kilometers at 60 kilometers an hour. 120 kilometers divided by your velocity, 60, takes you 2 hours to get there, or miles per hour if you want to do miles per hour. So with no wind, then, the total time is going to be the total time of our trip for one leg. It's the distance divided by the velocity, so just d divided by v sub p. So it's going to be d divided by the velocity of the plane. And then, of course, on the return leg, there's no wind involved. Same thing, plus d divided by the velocity of the plane, whatever it happens to be. And so clearly we can just add that together. We get 2d over v sub p. Okay, so that's the case. If there's no wind, we just need to know the distance. We need to know the velocity of the plane, and simple calculation to give us the total time it takes for the round trip for the plane. Now let's turn on the wind. Okay, so we've got the velocity of the wind coming here. And actually, at this point, for those of you who want to do a little quantitative challenge, or even just conceptually for everybody to think about this, you think, okay, on the trip up, the wind's going to be against the plane, so it's going to retard it. It's going to take a little longer. On the trip down, though, the wind's going to be helping the plane. Shouldn't it cancel out? In other words, shouldn't you get the same answer for the total time? Definitely you're going slower on the first leg of the trip, but then you're going faster on the second leg of the trip. So should it not just cancel out and we get the same result? as we will find, it's not quite that simple. And so you might think about why that might be. You can think about it just in a qualitative, conceptual fashion. But you can also think about it for those of you who want to, say, pause the video now and see if you can work this out. I'll get you started by saying the velocity on the first leg of the trip is going to be the velocity of the plane minus the velocity of the wind. Okay, so that's the net velocity on the first leg. And then we have our same equation involved here, distance divided by the velocity. And the velocity on the second leg of the trip is going to be the velocity of the plane plus the velocity of the wind, v sub p plus v sub w. We use vw for the wind. The equation is the same. You just have a different velocity on each leg now. The total time is going to be, add those two things up and get the total time. So again, if you'd like the little challenge and see if you can come up with what we're going to come up with here in a minute, so we can do it correctly, then go ahead, pause the video, and try that, and then come back, and we'll look at the details here. Okay, so the A to B trip, the time, what we're interested in here is the time for that, again, is going to be the distance, d, divided by the velocity, and the velocity going against the wind is v sub p minus v sub w. So it's going to be d over v sub p minus v sub w. Just same equation as before, just different velocity this time. And then the B to A trip is going to be distance d, but the velocity in this case is v sub plane plus the velocity of the wind. So here we got the time equals d v sub p plus the velocity of the wind. And the total time is just add those two things together. So the total time is going to be d plus vp minus vw plus d vp plus vw. Okay? And now what we'd like to do, here's where a little more of the algebra comes in, we'd like to simplify this a little bit. See if we can get it into a nicer form such that we can really compare it to this. Because remember, what we're maybe thinking here is that it should cancel out. Shouldn't this? It doesn't look quite like that, but shouldn't it maybe end up sort of like that? Well, it's going to end up not quite like that, but almost. So let's see if we can do that. So to do that, just to make some more room here, we're going to bring this up here. We'll leave this up here because we want that result there. So we're still working with the wind stuff here. Okay, so we're saying here the total time, just rewriting this thing here, is going to be d vp minus vw plus d vp plus vw. And at this point, we've done the analysis. Now we just have to crank through the algebra a little bit and see what the result is. So this is one of the reasons we did the math reminder here. We have two fractions. We want to add them together so we can combine them. We need to get common denominators, and the little trick we use is we multiply each in the form of 1, but with the other denominator. So here's what we're going to do. We're going to say this equals d over vp minus vw times the other denominator in the form of 1, vp plus vw over vp plus vw, like that. Okay, so I'm just taking this first term here, multiplying by 1, but in a special form here, and do the same thing for the second term, plus d over vp plus vw, because that's this term here, and now multiply it by 1 in the form of the other denominator, vp minus vw all over vp minus vw. So I have not changed anything. I can also multiply anything by 1 if I want, and results will still be the same. But now you see in the denominator I've got vp minus vw times vp plus vw over here. Same thing over here, but just in opposite order there. So let's put it all together and see what happens in the numerator. So we're going to get, here we get d times vp plus vw all over vp minus vw, vp plus vw. Actually, I really should extend this over, because I'm putting these two terms together. They both have the same denominator. That's this thing, just in a different order there, so I can flip it around. And then the second part of the numerator is plus d times Vp minus Vw. Okay, so I just combined them together. I haven't done anything else besides that here. But now I can look at the top and I can say, okay, I've got d times Vp and d times Vw. If I multiply that out. And over here I've got d times Vp, but I've also got d times minus Vw. So over here I've got a d times Vw. Over here I've got a d times minus Vw. They cancel out. I'll have dVw minus dVw. And I'm going to be left with d times Vp here and d times Vp here. So that's two of them. So I can write this as, try to squeeze it in down here, 2 times d times Vp all over Vp minus Vw times Vp plus Vw. And we're going to bring it up here in a minute as well. Okay, so see what we did? We just said, okay, here's our total time, that plus that for each leg. Put them together for a common denominator, and then noted that in the numerator, some of the terms cancel out. So I've got d times Vw and then minus d times Vw. So they go to 0, and I'm left with this. Okay, so now we'll bring this back up here. We'll leave that because that was our starting point. Okay, so what we've got so far then is 2d Vp over Vp minus Vw Vp plus Vw. So that's what we've got so far. Now let's, again, crank some more algebra here. Let's multiply this out in the denominator on the bottom here. So we'll leave the top as it is for a minute. 2d Vp. I've got a Vp squared. Vp times Vp is Vp squared. Minus Vw Vp plus Vw Vp. So those terms will cancel out. Minus Vw Vp here, and I've got a Vp times Vw plus Vw times Vp. And then minus Vw squared. If you've done algebra recently, you recognize immediately what we're going to get here, and that is this. Vp squared minus Vw squared on the bottom there. Okay, so okay, now what? Well, again, going back to the math review we did in the last video clip, we're going to factor out in the bottom here, we're going to factor out a Vp squared. Okay? And so it's going to look like this. We got 2d Vp. We haven't done anything on the top for a couple steps here. But on the bottom, we're going to write this as Vp squared times 1 minus Vw squared over Vp squared. Okay? I just pulled out the Vp squared term here, so that gives me the 1 there, and then on the other term, Vp squared times that would give me the Vw squared again, so they're identical there, they're equal. And the reason I did that is now I can cancel this Vp on the top. I've got a Vp on the top, I've got a Vp squared on the bottom, and so this thing then equals, we'll write it up here, 2d Vp, oops, sorry, not the Vp, that's what we're trying to get rid of, 2d on the top, that's what I've got left on top. On the bottom, I've left one Vp here, so I've got a Vp, and then the 1 minus Vw squared over Vp squared. And we'll rewrite this in just a second here, but let's see what we've got there. Okay? And another reason we did this is now we see, going back to the total time with no wind, it was 2d over Vp. I sort of almost have that. I have a 2d on the top in the numerator, a Vp on the bottom, but I've got that extra term there. And so let's just rewrite it so we can look at it closely here. So after a few steps of algebra there, we find the total time for with wind is going to be 2d over Vp. And then this second part of the term here, which is the 1 over 1 minus Vw squared over Vp squared. Like that. And all I did to go from here to here is just, write this part of the denominator as a separate factor there. And the reason I did that is to show very clearly, I had the 2d over vp here, 2d over vp, but it's not the same. I have an extra factor in here. So it turns out that when I've got the wind involved, going up and going back down, even though it's hurting going up, headwind, tailwind going back, it doesn't cancel out exactly. It actually is a difference with the wind involved such that you do not get your no wind time of travel for the round trip. You get a slightly different time. Note also that, and this is a good thing to check in these cases, you say, okay, this is the case with the wind involved. This equation should be true if there's no wind, right? Does it give us the right result? Well, if there's no wind, the velocity of the wind is 0. So this is 0, and I get 1 minus 0 here. Velocity of the plane is something. And then I get 1 divided by 1, so that's just 1, and I get 2d over vp, the answer I get with no wind. So this is a more general equation I have derived. It works with wind, but it also works if I've got VW equals 0 for the wind in there. So somewhat surprising result because, again, intuitively think, shouldn't it cancel out? But let's think about this in terms of doing conceptual ideas like this or conceptual problems like this. Sometimes it helps to take an extreme case. So let's take an extreme case here. Let's say the plane velocity is 300 kilometers per hour. Sort of a slow plane, actually, I suppose. Or 300 miles an hour if you want that, or whatever you want to use for the velocity of the plane. And let's say the wind, okay, so this is going to be VP. Let's say the wind is 299 kilometers per hour for the wind. Very strong wind, of course. Tornado wind, really. But again, it's just a thought experiment, like many thought experiments Einstein did. Maybe not quite sophisticated as some of his, but it's a thought experiment. Let's think about what happened here. Okay, just intuitively. So going up, the effective net velocity of the plane would be 300 minus 299. It'd be 1 kilometer per hour, okay, if it really could fly like that. So it'd be a very slow trip going up. And then on the way back down, the velocities would be 599 kilometers per hour. So about twice as fast. But by doing that, you can see, it's going twice as fast going down, but it's not just going half as fast going up. It's going about 299 times slower than it did before. So it's not an equal situation in terms of going against the wind and coming back with the wind. You can double your speed in this case, going with the wind, but you're slowed down many more times than just the doubling you get, much less than half the speed. And therefore you see that, yes, there's a significant difference when the wind is involved. Okay? So the point being here, how does this apply back to the Michelson Morley experiment? Well, in this case, essentially, this would work for light as well if there's a light medium, if the ether exists. Okay? So in other words, it'd be like sending a light beam against the ether wind and then sending a light beam with the ether wind. And if you could somehow see that difference in speed and detect it, then you could actually prove the ether exists or investigate the properties of the ether a little bit more. The problem is that the velocity of the Earth through, as it rotates around the sun, is about 30,000 meters per second, something like that. And that's still much, much less than the velocity of light. And so the effect, notice that when the velocity of the wind here is much less than the velocity of the plane, there's not much effect on the travel time. And that's the case with, even though the Earth moves around the sun at a relatively fast speed for most of what we're used to, certainly, that the velocity of light is so much greater than that this is a very small factor in here, and this is essentially 1, and therefore it's very difficult to see any effect. It does exist, it's very tiny, but with the experimental techniques they had, they weren't able to do it just from that alone. So they actually added on to this idea, and here's what they did, and that'll be the subject of our next part 3 for our video clips here. But essentially they said, okay, we'll do one up and back like this against the wind, but let's analyze the case where it's crosswind. So if the airplane or the light beam is going this way and the wind, whether the regular wind or the ether wind is going crossways against it, what happens in that situation? So we'll analyze that and then compare this situation with that situation and see what we can get out of it.